Okay, so chemical equilibrium. Let's go ahead and talk about this, and I'm gonna follow along in the book to make sure I'm not missing anything while I do this, because these notes may or may not be exactly what I was looking for. So equilibrium. I like this stuff. I think it's cool. You are either going to think it's cool or you're going to think it's really hard. One of the two. Or both, actually. I guess it could be both. But I don't think you're going to think that it's easy. And I don't think that you're going to think that it's not cool. Well, I suppose you could. All right, anyway. Let's move on. So, chemical equilibrium. The law of mass action is an important law for equilibrium. It comes in a little bit later. There's a couple scientists if you're interested. So the first thing that we need to realize here, we have talked almost exclusively up to this point about reactions that happen in one direction, right? So, I mean, a good example of that is a typical combustion reaction. You've got CH4 plus O2. Yields CO2 plus H2O, and I know that's not balanced. I'm not going to balance it right now. But that's a reaction that really only happens one way most of the time. This does not typically go back this direction because it's not favorable to do that. Okay, there's a, I guess if I was drawing the activation energy diagram from, or the potential diagram from the last unit, it would look something like this. All right, so just a tiny little hill to get over to get this thing started, right? But if you're trying to go back in the other direction, if you're going this way, that's an enormous hill to make it up, right? So it just doesn't usually happen that way. But there are reactions that are quite a bit more reversible than that, where you can go back in the opposite direction, okay? The products can react to reform the reactants. And that's a huge category of chemistry that we have not really covered up to this point. So kind of like kinetics is a huge area of chemistry that we hadn't covered up until the last. Basically, we're just covering huge parts of chemistry we haven't covered yet for the rest of the year. So, which is good because, I mean, I get bored of the same stuff over and over again. The first semester is a little repetitive. So hopefully this at least keeps things interesting. So chemical equilibrium. If we have a chemical equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, and the concentrations then don't change. Okay? So we did actually talk a little bit about rates in a forward and reverse direction when we were talking about how to write the rate law for a mechanism in the last unit. So you got a little bit of an introduction there. So basically equilibrium means if we've got a reaction that's going from reactants to products and products to reactants at exactly the same rate, that's an equilibrium. Okay? Now in chemistry, I think the book talks about two types of equilibrium, a static equilibrium and a dynamic equilibrium. In chemistry, it's always going to be dynamic equilibrium. Okay? And what does dynamic mean? Moving. Okay? So it's not that nothing's happening. It's just that the forward reaction and the backwards reaction are happening at exactly the same rate, so there's no overall change in concentration, right? So you've got A over here, you've got B over here. A is changing to B just as fast as B is changing to A, so it looks like nothing's occurring, but really something is. And we've talked about this a little bit already in terms of a saturated solution. Remember that in the last semester, where really in a saturated solution, you've got particles that are redissolving at exactly the same rate as particles that are precipitating out of the solution. So it looks like you've just got a solid sitting down there, but really there's something going on, okay? So that's what chemical equilibrium really is, okay? An example of that, kind of a weird example, but mercury oxide in equilibrium with mercury and oxygen. So arrows going both directions indicate equilibrium. Now another way that you will often see this is half arrows. Okay, so just kind of get used to that. That's another way that they show equilibrium quite a bit. So either one of those things basically means we've got an equilibrium. Okay? So physical equilibrium, is this the one that I wasn't going to use and then I ended up using anyway? Oh well. Okay, so physical equilibrium, I guess, it's not just a chemical thing. You can have a physical equilibrium, which I just talked about that with dissolving, right? Okay, that's a physical equilibrium. Or a gas changing to a liquid, liquid changing to a gas. At 0 degrees Celsius, you actually have a solid-liquid equilibrium with ice and water, right? So if you're right at 0 degrees, then you've got just as much ice changing to water as you have water changing to ice. So it's in perfect equilibrium, and that's just a physical thing, okay? Now, this is an important diagram, okay? They specifically mentioned this one on the AP exam that you need to know this. The idea here is the concentrations of these things are changing over time until they don't, right? So what can I say when these lines all flatten out? What can I say about the reaction at that point? It has reached equilibrium, right? This is the concentration over on the left side, or on the y-axis, time on the x-axis. So as this reaction proceeds, notice the NO2, which is the reactant here, it's decreasing in concentration. By the way, let's pull kinetics back into this. Is this the first order, or sorry, a 0 order reaction? Definitely not a 0 order, right? Because concentration versus time does not give us a straight line. So we know it's something other than 0 order for the mechanism here. But this thing decreases in concentration until eventually we have produced enough of the O2 and the NO that they start producing back in the other direction, okay? So at that point, right about here where the lines flatten out, we're at equilibrium, okay? Now, again, that doesn't mean nothing's happening. It just means that the NO and the O2 are changing back to NO2 just as fast as the NO2 is breaking down into the NO and the O2. Okay? Another example of a reversible reaction, N2O4 and NO2. And this one's kind of cool because you can actually see the color. So if it's N2O4, it's colorless. As it changes to NO2, it turns brown. Okay? And so then, again, you could start with different concentrations of these, and you could watch the results of the reaction. Let's see here. What is it saying? Color of the molecules can be used in chemical equilibrium in order to show that the concentration will remain the same over time yeah, so I mean this is basically the same graph that we just talked about. So in the first scenario here, you only have NO2 present to begin with. Okay, so then the NO2 concentration decreases, the N2O4 concentration increases until they reach equilibrium. In the second scenario, you only have N2O4, and again, you have a decrease of one, increase of the other. And in the third scenario, you've got both of them present, but evidently you had a little bit more of the NO2 than you needed, so that starts to drop in concentration while the N2O4 raises in concentration. Okay? All right, so then let me make sure there's not anything else that we need to cover in that stuff. I guess the one thing that they don't really talk about in these notes that's in the book is how the
please contact the attendance office.
How the rate constant.
Please report to
oh no, I'm sorry. There it is. It's right here. Yeah. So this is the equilibrium constant. Okay. So this is how the rate constant is very much related to equilibrium. Okay. Because remember, equilibrium is all about rate. It's about a forward and a reverse reaction happening at exactly the same rate. Okay? So you've got a forward reaction, A to B. The rate would be Kf times the concentration of A. Okay? And then Kf, again, is the rate constant for the forward reaction. For a reverse reaction, B to A, the rate is Kr. That just stands for reverse. The reverse reaction times the concentration of B. Okay? So, if you want to derive the equilibrium constant, doing a little bit of rearranging here, And why are they going from concentration to pressure all of a sudden? Oh, okay, they're figuring out molarity equals P over RT. Sorry, my notes do not match up very well with the book this time around. But, okay, they do talk about Kp and Kc in section 2, so that's something we do need to cover. So the concentration of A is the pressure of A over RT. Now, the reason for that is because over here, they just rearranged the PV equals nRT equation, okay? Now, remember, moles over volume, moles over liters, is equal to molarity, okay? So molarity is equal to pressure over the R times T. So you use PV equals nRT, kind of rearrange that to relate concentration to pressure, okay? So if I want to put this in terms of pressure, my concentration of A is equal to the pressure of A over RT, and my concentration of B is equal to the pressure of B over RT. So you can rewrite your rate equations, plug in the PA over RT part right here, where we did have the concentration of A, and the PB over RT part here. Okay? Now, this is really the important part. You can do this with concentration too. I don't quite understand why they started doing it with the pressures like this. You can do this with the concentration. The forward rate is equal to the reverse rate, right? So if this and this are equal to one another, then you can set Kf PA over RT equal to Kr PB over RT. Okay? And you can rewrite that, cancel terms. PB over PA equals Kf over Kr. Okay? Now, these are just two rate constants. If you take two constants divided by one another, you get a constant, right? And so we're going to call that, we're going to give that a special name. We're going to call it the equilibrium constant. All right? Let me back up here a little bit and show you how this works with concentration. Okay, it's a little bit easier with concentration here. The rate of these two reactions are equal to one another, right, at equilibrium. So then we could also say that Kf times the concentration of A is equal to Kr times the concentration of B. Those two rates are exactly the same. All right. So then if I want to get the rate constants on the same side as one another, so that, again, I can call it an equilibrium constant, then I would basically just divide both sides by A. Actually, it's a little bit arbitrary which side you divide by here when I'm deriving this. So Kf over Kr is equal to concentration of B over the concentration of A. All right, and again, Kf over Kr, we could just call that the equilibrium constant, okay? So at equilibrium, that's going to be a constant value. And it doesn't matter really what the concentrations of B and A are. If the concentration of B changes, the concentration of A will have to change in a certain way so that this equilibrium constant stays the same, okay? And at any given temperature, that is your equilibrium constant, okay? What do I want to say about this? See, they kind of jumped forward here. Now, so I guess what I want you to notice, this is going to be very disjointed. Equilibrium constant can be looked at in terms of concentrations, like it is there. It can also be looked at in terms of pressures, like it is over here, PB over PA, okay? So the two main situations where we're going to focus on equilibrium is in situations where we're dealing with gases, and then in situations where we're dealing with things that are in solution, okay? Those are the two situations where we're really going to focus on the equilibrium constants, okay? This table is showing experimental data, and this is in the book too, so this is kind of useful. For the NO2 N2O4 system, that's the colorless brown system that you were looking at earlier. Okay, so we've got concentration of NO2, concentration of N2O4 initially. Then we've got our equilibrium concentrations, okay? And then we also have our ratio of concentrations at equilibrium. Okay, so notice something here. The equilibrium concentrations, there's not a lot of a consistent pattern there, okay? But if you take the ratios of the concentrations, well, that doesn't work out very well, NO2 over N2O4, because we just said, find your equilibrium constant, you need to take, the product over the reactant, right? But that doesn't really do much for us here. I mean, these numbers seem like they're all over the place. But when we square the NO2 and divide the N2O4, divide it by the N2O4, it gives us basically the same number every time, okay, regardless of what initial concentrations we start out with. So that's kind of interesting. Now, if we look back at that reaction, is this the same reaction? Okay, sorry. That's why. Do I have that reaction written anywhere? Did it? One more back? Oh, okay, there we go. Thank you. I knew it was somewhere on here. Okay, here's what I was looking for. There's a coefficient there, okay? So in the last chapter, I basically trained you that you can't figure out a rate law based on the stoichiometry in a reaction. Now you're going to kind of have to untrain your brain on that a little bit, because you can actually figure out the equilibrium constant expression based on the stoichiometry of an equation. All right? So notice, we squared the NO2 because there was a coefficient 2 in front of the NO2 in the equation. Okay? There was just a coefficient 1 for the N2O4, so that's just raised to the first power. All right? So, yeah, there we go. The exponent 2 for the NO2 in this expression is the same as the stoichiometric coefficient for the NO2. I should have just gone forward a slide instead of going back several. So here's the general way to write an equilibrium expression. If you've got A plus B is C plus D, and then you've got coefficients A, B, C, and D in front of those, when you write the equilibrium expression, it's going to be products over reactants, okay? And then you raise the products to whatever power the power that you raise it to is the coefficient in front of that product. Okay, so C to the little c power, D to the little d power, over A to the little a times B to the little b power. All right, so it's actually, you're going to be able, you're not going to have any trouble writing these equilibrium expressions. They're actually very easy. Now the trick will be knowing what they actually tell you. Okay, which is that in this unit? No, it is not. Okay, so we'll cover that next time. We'll talk a bit more about what does it actually tell you when the K is large or when the K is small. Okay, but here's your expression. Okay, K equals C to the C power times D to the D power over A to the A power times B to the B power, where K is the equilibrium constant and it is unitless, okay? I'm not sure if I need to go into a lot of detail about why it's unitless, because it's not on the new AP exam. If you're curious about that, you could ask me about it. It has to do with the fact that these ultimately are not really concentrations that you're plugging into the equilibrium expression. They are called activities, okay? And so, I mean, if you're interested in that, we can talk more about it later. But what you just need to know is that the K is unitless. All right, doesn't have units. So this is one time when you do not want to put your units. And that's even more confusing because this is a big K. Guess what they make a big deal about for little k on the AP exam? The units, right? Little k, the rate constant, you have to know what the units are. They ask that question all the time. Big K, there are no units. All right? So, good luck keeping all that straight. Okay, and this is the magnitude of the equilibrium expression stuff that we will talk about next time. One thing I will mention here that is not on these notes unless it's further along. Let me see. Yeah, I'm not seeing it. Okay, let me back up a little bit. So notice here, I wrote the equilibrium expression in terms of concentration. I also wrote it in terms of pressure. Okay? So when you write the equilibrium expression in terms of concentration, sometimes you can put a little C down there just to say, all right, this is the equilibrium expression with respect to concentration. If you're writing the equilibrium expression with respect to pressure, you can write a Kp. All right? And the way to relate those to one another, it's actually in the book. The equation is Kp equals Kc times RT to the delta N power. Okay? And the delta N is actually the change in the number of moles from one side of the reaction to the other. So you count up the number of moles of product you have minus the number of moles of reactant. And actually, it's just the gas moles of product and reactant. Okay? Now, the reason I'm not making a big deal about this is because they actually took this equation off of the AP equation sheet this year. So my guess is they're not really concerned that you know how to relate Kp and Kc anymore. All right? Just be aware that there is a difference in value between those two numbers. If you measure the equilibrium constant with respect to concentration, you would get a little bit different number than with respect to pressure, but this is the way that you could actually convert from one to another. Okay? But I'm mentioning that just so that you've seen Kc and Kp. I don't think that they're going to put that on the AP exam, though. All right? I think 15.3 is where we're really going to get into some better stuff about the equilibrium constant. So that's basically all we need to talk about for now as far as what equilibrium actually is. Okay? So the important things here to realize, this is, I mean, if I could kind of underline any statement from the first two sections here that I think is important, it's the understanding that at equilibrium, the forward rate of reaction equals the reverse rate. Okay? And so when you're thinking about your rate laws, you can write two rate laws, you relate them to one another, and that's how you actually end up getting the equilibrium expression, is by those two rate laws, the forward and reverse. Okay? So that's where equilibrium comes from. That's where the equilibrium constant K comes from. It's actually related to rates of reaction. And you just need to understand that reactions can happen in both directions, I guess. It's pretty easy. So I would work your way through some of the book stuff. They might have some other things there. But other than that, really, the good stuff starts when we start talking about what K actually means, what it actually tells you, and that's the next one. So, all right, have a good long weekend. We'll see you guys on Tuesday.